Morning, everybody. Sometimes you just gotta turn yourself around. Second half of the semester, we'll be facing this way. And we'll also be facing such things as what is in chapter 21. So with that in mind, the title of chapter 21 is Aromaticity. And aromaticity has really nothing to do with smell, although many organic compounds that are aromatic do smell. Most of these have a distinguishing odor, with some exceptions. Benzene found in gasoline in small amounts. We don't want large amounts. It's not that good for us. Toluene is methylbenzene. All of these common names, as you will read in the textbook, you need to learn them because they are that common. Pyridine we've been using before. A little preview here. Another name for pyridine is azabenzene. Aza is used to indicate that a nitrogen has replaced a carbon. So it is a good nomenclature tidbit to know for the rest of our organic chemistry naming careers. Phenol we studied in chapter 10. It's an unusual alcohol with a pKa of 10. Aniline is aminobenzene. It is a precursor for many dyes, that's colored compounds. Benzaldehyde, the principal component of almond extract, the one that gives almonds their unique flavor and taste. Benzoic acid is an aromatic that is odorless. Main reason is it's a solid, but that doesn't stop things like naphthalene from having a strong odor. Naphthalene, with its low intermolecular forces, goes straight from solid to gas. That's called sublimation and gives off an odor that smells like your grandmother's cedar closet, where she has mothballs in there. And this is the old school mothballs, naphthalene here. So learn all of those, and then we'll learn why they all belong in this chapter. We have guidelines for establishing, is a molecule aromatic or is it not? And the guidelines are as follows. You must have a cyclic molecule to be considered aromatic. There must be a special number of pi electrons. This number can be solved with the equation 4n plus 2. If you use an integer n, then that gives you the possibilities for the number of pi electrons in an aromatic compound. If you do not have that number of pi electrons, you are not a candidate for aromaticity. For example, we seem to have a label of n equals for every molecule. If n equals 1, then 4n plus 2 equals 4 times 1 plus 2 is 6. And we count 6 pi electrons, 2, 4, 6. So benzene, according to rule 2, is a candidate for aromaticity. Naphthalene, if n equals 2, then 4n plus 2 is 10, and we do have that number here. And that is a candidate for aromaticity. Notice I keep saying candidate. There's other rules, and they must all be satisfied. Anthracene is a candidate. It solves for n equals 3, as does phenanthrene. 14-annuline does qualify, although it has other issues that make it a not a very good candidate for aromaticity. We'll talk about those shortly. 18-annuline is a perfectly aromatic compound. Has 9 pi bonds, 18 pi electrons. Here's a personal note down here. You'll see this symbol used a lot for benzene. I am not a fan. It's more my personal preference to not draw it like that. For this reason, I like to see the number of pi electrons to determine if something's aromatic, and a circle doesn't say anything to me about the number of pi electrons. So this little lug nut is a pet peeve of mine. I don't like seeing it, but I'll put up with it. More rules. The molecule must be flat. So if you remember your geometries and hybridizations, then sp2, which is trigonal planar, is certainly flat. sp, which is linear, a line, is definitely flat. Those are your two possible hybridizations for being flat. And the main reason is not necessarily the hybridization, it's the availability of an orbital to use for resonance with those pi electrons we talked about in number 2. You cannot resonate pi electrons unless those electrons are in p orbitals. As you remember, p makes pi. And then kind of follows this. It's almost an unnecessary rule. If all of the atoms have p orbitals, then they can resonate. I mean, that's 3 takes care of 4. So guidelines for aromaticity, and we have to be able to determine if molecules are aromatic or not. I don't know why I created a new page. It must be this new surroundings here. All right, we have some molecules that are not aromatic, and we are using the rules to explain why. If you go back to your rules of number of pi electrons, remember what qualifies as an integer. Yes, 0 qualifies. So you're asking yourself, when could I ever have 4 times 0 plus 2 is 2 pi electrons and still be a cycle? Well, rules 1 and 2 are followed for our first molecule here, but rule 4, this can't be flat. Sorry, it can be flat because of the incredible strain here, but it's an sp3 carbon. So it can't resonate. You can't resonate sigma bonds. You would have to break them. Okay, so even though it's flat, it's not a resonator. You don't have a p orbital to resonate with the pi electrons. 10-annuline, a very small annuline. What's an annuline, you're saying? Annulines are single ring, aromatic compounds. Nobody calls benzene 6-annuline, but if they did, they would not be making a mistake. 6-annuline is an acceptable name for benzene. Organic chemists will look at you funny and say, you're playing a joke like dihydrogen monoxide. But it's okay. It follows the pattern. So we have annuline here. This is not an annuline. There's more than one ring. Same here. But these are all one big ring. They qualify in the annuline family. 10-annuline qualifies as an annuline, but it's not aromatic because if this thing is flat here and here, then these H's would be on top of each other, which is not possible. You can't have two atoms in the same space. So this thing would have to bend to get the H's away from each other. And as it bends, it's no longer flat. So if you're forced to put atoms on top of each other to be flat, then that is preventing you from becoming aromatic. And we go back and say, or ask, why is naphthalene not suffering from the same thing? The answer is this is perfectly fine to have this carbon real close to this carbon. There's no atoms on top of each other here. This is just a perfectly fine sigma bond. And in another resonance form, there'll be a pi bond there as well. So yes, perfectly fine here. Not perfectly fine when you're putting two H's on top of each other. This guy has the right number of pi electrons, but can't resonate in a circle. So that's not aromatic. This has the right number of pi electrons, 2, 4, 6. Then we solve the equation with n equals 1 with an integer 1. But this thing here being sp3 means the pi electrons cannot resonate through this position here because that's not a resonating atom, not without a p orbital. And then we move on to molecules that are called anti-aromatic, which are clearly not aromatic as well, for the reason being they have the wrong number of pi electrons. Now this has 8 pi electrons, clearly 2, 4, 6, 8. So if it resonates, it's resonating 8 electrons in a circle. And that would involve solving the equation with n equals 1.5. 4 times 1.5 plus 2 is 8. And that's not aromatic. A good question that's a little beyond the scope of this course is, why is that a bad thing? And the answer lies with the fact that as you resonate in a circle, electrons are always moving in waves, just like light. And waves tend to constructively interfere with each other if they're in phase. I got my two hands going like this. Those are waves that are in phase with each other. That's a stabilizing influence. But if one wave meets up with another wave, and we're looking at wave here cresting when this one is troughing, and they meet, that's destructive interferences. Those waves are not interested in interacting with each other. They would rather stay independent of each other and not resonate with each other. And it's a whole big hand waving phase argument that we will never get into on tests. You just have to believe the 4n+2 rule is a reality and use it to describe if molecules are aromatic or not. This molecule, because the waves of the phases, of the resonating electrons as they meet around the other side would be out of phase. This molecule puts all of its pi electrons in a way where they cannot resonate with each other. It's not flat. These are isolated pi electrons, no stability due to resonance. And that's what that molecule looks like because of that. Pretty consequential, isn't it? 12-annuline has the wrong number of pi electrons. It will not go flat. It will not be aromatic, as the same problem with 16-annuline. So there you go. So we have questions sometimes, how can you have 2 pi electrons and be aromatic? Well, let's fix that sp3 carbon, shall we? If that sp3 carbon is not really a sp3, but it's sp2 as a carbocation, I want you to remember sp2 has an empty, yes, p orbital. P orbitals can resonate with other p electrons. So this sp2 cation, although incredibly unstable due to strain, is stabilized by this special kind of resonance called aromaticity. Aromaticity resonance is very special. And that's not the only resonance form, is it? We don't have one where the pi electrons are up here. So we'll have 3 equal resonance forms. And there's the pi. And this is going to exist for a very short amount of time on this screen. Oh, I don't even like doing it. That represents the average of the 3 resonance forms. I'm going to get rid of it. I don't like it. It's got a circle in it. Doesn't mean it's wrong. It just doesn't show me enough information. So this is an aromatic cation. I wonder if we can have an aromatic anion. We'll talk about that very shortly. Here's a big question up here. To rehybridize or not to rehybridize? It's a good question. Got a little Shakespearean on you there. Let's go back. Let's look at normal old amines that we encountered way back in our first chapter, and we'll have their own chapter at the end of this test material, test 3. An amine, if you look technically at the definition of a stereocenter, if the amine has 4 different groups on it, which this one does, let me outline the 4 different groups. We have an ethyl, we have a methyl, we have a hydrogen, and yes, a lone pair which contributes to the geometry has to be considered a group. And why would it be priority number 4 using the RS rules, the Kahn-Ingold-Prelog rules of stereochemical determination? Well, it has a mass of very close to 0 grams per mole, which makes it the lightest substituent on this nitrogen. Much lighter, 2,000 times lighter than a hydrogen atom. So I've prioritized the items 1, 2, 3, 4. The number 4 is not on a dash, so I did a double switch. I just used a stick to represent the direction of the lone pair. And I switched the 4 with the 1 to get the 4 on a dash. And that's an R stereocenter when I switched the 2 and the 3 as well. So we never talked about stereocenters on nitrogens before for a good reason. The barrier for this, if you follow this with a potential energy diagram, going from one species to the other, this nitrogen really likes being sp3. It's got a barrier to get up to the sp2, and then a symmetrical barrier getting down to the other sp3. And the questions are, why are these so much more stable on the outside than the one in the middle? And the answer is quite simple. This is potential energy. And this is rehybridization here. We're rehybridizing to sp2 so that we can get to the other sp3. And you'll see as it rehybridizes, this ends up rotating to here and becoming a p orbital. And then the rotation continues downwards. So downwards through here to get to here. And we have the other hybrid over here, sp3. Well, the question was, I forgot my own question. The question was, why are the 2 ends more stable than the one in the middle? And if you are in a hybrid, that means it's 25% S. And when you're in a p orbital, that is 0% S. You have no S in your nature at all. I made 0 into a sigma. 0% S. Which has the lone pair closer to the nucleus? Definitely the hybrid. Why does this happen constantly? This thing's happening thousands of times per second. So that kind of answers the question at the top of the screen. If a secondary amine has a nitrogen stereocenter, which is the case here, then why is it not named RS? Well, you wait a nanosecond and the R just became S, and then you wait another nanosecond and the S became R, and this thing just, it's rehybridizing so fast it makes your head spin. So we're not going to say it's one or the other. It spends half its time R and half of its time S. That's it. And then we have another question up here. Why are amides considered to be trigonal planar when the nitrogen is sp3? It looks sp3. We'll answer that one in orange. This is a very common discussion for things like amino acids. And we'll just do it like this to keep it generic. Well, when you have atoms that have lone pairs, the only way they can do this which is called resonance, is you must rehybridize first. So that process on the left of the screen has to happen first before you do the resonance. Must rehybridize to p orbital. So it means the nitrogen is going to go to sp2. Remember, it's only p orbitals that can resonate with other p orbitals. Maybe you didn't know that. So that would answer the question. In the other resonance form, which is not quite as stable, it's got a couple charges. So I'd have to say it spends a lot more of its time back there than over here. Double bond and an O minus. Got two charges. That's one reason it's less stable. But it is a contributing resonance form. O minus is not a terrible anion. N plus, not great, but not terrible. So you'll notice the geometry of a lot of amides is trigonal planar, because this is a contributing resonance form. And that answers the orange question. And it seems to me we have a green question. In furan, how would one of oxygen's lone pairs rehybridize and not the other? Well, we'll use the lengthier discussion that's found right in our textbook. This should be our green answer. Maybe I'll recolor the box green. Wish me luck on that one. And give it a shot. You have to have a steady hand. I got high hopes. Not bad. There. So we're answering the green question with our green box. And here is Phenol, a close relative of furan. And we have to learn both of these, please. In the text, it says somewhere, not in the box here, it says to learn these two structures, Phenol and furan. They are very commonly found in both organic and biochemistry. And Phenol, in its sp3 configuration, does not qualify as an aromatic compound. If it's sp3, then these are not considered pi electrons. They're in a hybrid. So you only have 4 pi electrons, and this thing will not be aromatic. I want it to be aromatic if it can. What you're going to do is rehybridize it so it's this kind of nitrogen here, and I redrew it here. And why would that happen? It happens because now this molecule can resonate in a circle. And that would definitely lower the barrier of rehybridizing for this diagram to much lower, because this molecule is stabilized by what? What's it called again? Special kind of stability where you have the right number of pi electrons. You're flat. Every atom can resonate. What's that called? This kind of resonance? It's called aromaticity. It's the topic of the chapter. It rehybridizes so it can achieve aromaticity. It has 6 pi electrons now. It has the 2 pi bonds for 4 and the pi electrons in this new p orbital, which can resonate. So you can draw yourself 5 different resonance forms for this. And there's the other sp3. This molecule, unlike up here, I would say this line is down here. Do you want to do a quick sketch of the diagram for this one in green? Let's do it. I guess I don't know where to put it. I want to have it on above the other diagram. I think it'll be very illustrative for a good finish of this segment. You got your potential energy. Let's move it over to the left a little. And in this one, you're going to be here, going way down here, and then up to here. And this would be for this species here. Why is it less stable than this species here? Well, the one on the left can't resonate with aromaticity. So this process definitely favors the sp2 hybrid. And the process up here, we're going to spend very little time with the sp2 hybrid because we didn't get any special stabilization of that pair of electrons. In fact, they got destabilized by being further from the nucleus. These got stabilized by being able to resonate with all the other pi electrons. And I think that's a good close for our first segment. I'll see you very shortly.